Okay. Awesome. Thank you very much. So hello, everyone. Thank you for joining our talk today, titled, Do We Really Need Deep Learning for Demand Forecasting? So a quick look at today's agenda. We will first introduce ourselves, and then we will give a high-level overview of who is Kinaxis, what they do, and what kind of product they sell, and then explain what us as a team, how us as a team are building a data product for demand forecasting. And once that is done, we will start with our analysis comparing boosted trees to deep learning for forecasting. More specifically, we'll talk about performance, cost, and explainability. So a little about myself. My name is Khanafer. I'm a machine learning developer at Kinaxis. I've been here for about 8 months working on our demand forecasting solution or enhancing our forecasting solution. But apart from machine learning and data science, I love to play soccer and I love to write.
And with Ali presenting as Sudhan, and I'm a machine learning developer at Kinaxis too. I love my food and cricket.
So first we'll introduce the product. So what do we do? Who is Kinaxis? We build a supply chain optimizer. We are a software company building supply chain optimization product called Rapid Response. Now, supply chain optimization is a big problem with many different teams involved, many different knowledge sets needed to solve the problem. But today we will be focusing on what us as a team do, which is demand forecasting. Now, first thing I like to do is define what is demand. And very simply, I will define demand as how much stuff will people buy from me tomorrow. Now, I use the term stuff because the stuff that we are forecasting demand for will depend on the type of customer that we have. For example, a manufacturing customer, computing demand for a manufacturing customer who is selling to retailers will come with different nuances than computing demand for a retail customer selling directly to a customer. And so I want to emphasize the word prediction. I'm saying predict demand because this is a machine learning problem model that we are trying to solve with data. And so the idea is to build a machine learning model that predicts how much stuff people will buy from that firm. Another complexity that comes along with this demand forecasting problem is how do we make it generic enough so that one solution works for all of our customers. So there's a high-level overview of who we are and what we do. Sudhan will dive a little deeper into how a data scientist looks at such a problem.
All right, so how does a data scientist look at that problem? So what we do here is we build a machine learning supervised model which predicts a target. The target here being the product's demand in the future. So now a product's demand is not something which we can measure. So what we do is we surrogate that by a proxy of quantity of that product being sold in the past. So now we have an pipeline wherein like our retail customers kind of feeds us or streams us all of their sales data. And that's just not enough to predict demand. So what we look at, what other stuffs which would drive and products demand up. So once there is this cost, the cost of a product that would drive the demand. And then we have other factors like promotions on a product or current campaigns being run or other supply chain planning interventions which are possible. And there are like other factors which are non-intervention, something like the product descriptions, the stores, the seasonality, the weather. So is there any event which is happening in the locality? And so that we have a lot of these data which we will want to fit into a model. So for that, what we do is we kind of get all this data, assemble them on tables, and then kind of join them up into one huge data frame. And on that data frame, we would want to perform a lot of aggregation functions. So that depends on what kind of forecast the customer is asking us. So are they asking demand for the next week or next month? So or for the next year? So you have like different, or can be for every hour for hourly forecast. So depending upon the ask of the customer, we would want to aggregate that data at different levels and then feed it to a model and then make a prediction. So that's what the data, as a data scientist, we kind of do to kind of measure products' future demand. Now, now that we are speaking of a model, what do we consider as a good model? So for a model to be considered good, so there is three main factors which we primarily look at. So there is one, done quickly. So we have like service level agreement with customers, and then there are agreements which says that we would have to kind of spin models every week. So when you have an demand for a weekly model, we would want our models to be trained within a few hours or maximum a day. And then there is low cost. We want the models to be trained fast and not use a lot of resources, computing resources, and also high quality prediction. So we want the model to predict future demand as close as possible. Now, beyond these three self-contradictory objectives, there's one more other use parameter which we would want to get right, is the explainability of the model. So now having a model explainable and we are able to explain the predictions to the customer kind of drives this confidence on our prediction model up, and then that drives our product acceptance with the customer. So nowadays customers are no longer ready to accept back box results. So yeah, so that's another factor which we want to get right. And I give up to Ali to explain on one of our favorite models, the boosted trees.
Awesome. So we can start our analysis between boosted trees and deep learning models. Personally, our team loves boosted trees because the way we get our data is very dirty. It has a lot of nulls, missing time steps, a bunch of zeros, etc. And boosted trees have proven to be able to handle these types of situations very well as proven to have very good performance on tabular data. Apart from that, they're easy to tune, easy to train, and easy to deploy. In terms of accuracy, we normally hit around an 80% accuracy when we work with boosted trees. But just like Sudhan mentioned, quality is really not the most important thing when you're comparing to things like cost, explainability, and time. So here we kind of broke down the cost for boosted trees. I just want to mention that this time is measured using a sample synthetic data, just so we're able to compare with deep learning models later down the line. And we kind of broke it down into how much every step of the machine learning pipeline takes to complete. We're ignoring hyperparameter tuning because that's often set we often just have one value, for example, like 6 hours, and we have it terminated by then, so that doesn't take too much time. But for things like feed generation and training, we run that about 4 times a month. And so we see here the breakdown. Feed generation takes about 4 hours, training takes about 9 hours. We do that 4 times a month. And so if we compute that, if we multiply that by the cost of a 32 gigabyte machine with 8 cores, we end up with about $87 per month. Next slide, please, Jessie. And finally, in terms of explainability, boosted trees can become hard to inherently explain if they're too deep, too interactive, have too many parameters. However, they do come with built-in feature importance parameters that will give you some insight into what is increasing your prediction or what is decreasing your prediction at a feature level. Otherwise, you can use some post hoc explainable libraries such as SHAP, which again will give you some understanding and meaning of a variable's impact on the forecast. For example, I have an image here that shows which one of these features will impact positively our forecast relative to a base value, and which ones will impact our forecast at a negative value relative to our base value.
All right, so up to the next content, deep learning models. So we know that deep learning achieves state-of-art performance on very high-dimensional data, say like images, text, etc. But then on tabular data, we have known that deep learning models kind of underperforms when compared to boosted trees. And then, as explained before, like most of our data is it's all tabular. And apart from that, I'll also have to mention the training, the hyperparameter tuning, and the deployment cost associated with deep learning models are generally higher, and it is difficult. And continuing on deep learning models, we know that deep learning, next slide, please. All right, so and on deep learning models, like its performance increases with the amount of data you can give in. So when you have really deep networks, you kind of have high degrees of performance, but then those to train those really deep networks, you need really huge amount of data. And in practice, not all use cases comes up with such huge amount of data. And then of course that you can indeed train shallow networks to kind of address smaller use cases, but then you would still want to do a lot of pre-processing and feature engineering for those shallow networks to be effective and on par. And yeah, so another aspect of deep learning which is most spoken about is that it is not inherently explainable. Of course, then you can use black box methods like SHAP to do some kind of explainability on deep learning models. But then considering that you are already on an SLA, and then deep learning is going to take a lot of time to just train the model, running off and post hoc methods like SHAP adds to its time and cost complexity. That being said, of late there has been interesting architectures like fusion transformers, which kind of use self-attention to kind of give you an explainability on neural networks in time forecasting. And those are things which we here at Kinaxis are exploring to add to our products in future. And yeah, so coming to the cost of building a model like on a sample synthetic data set for which we used to compare boosted models, boosted tree models and deep learning models. We used larger missions, like 112 gig memory with 1 GPU, and then it took quite a lot of, it took about 21 hours to finish training at a cost of $8.64 per hour. The total cost is, it's about 10 times more than what you would spend for and boosted tree model. So on conclusion, so what is the question at hand? Do we really need deep learning models for time series forecasting? The short answer is it depends. So like as we mentioned multiple times, model performance metrics alone doesn't capture the whole picture. We also need to look at the training costs, the deployment ease, the explainability when it comes to choice of the model. So that being said, boosted tree models performs way better on tabular panel data, especially when forecasting demand. And in most cases, currently that's preferable to any deep learning models currently. So yeah, so that's our take on that. And thank you for your time for listening, and we are open for questions, please.
Excellent, thank you so much. And we have 5 minutes of questions. If I mean, I have one question myself. If you can elaborate, please, more on the model performance and any challenges around around the behavior of the model under different conditions.
Right. So
I mean, how do you evaluate? What was the metric you used to evaluate the performance of the model? Did you?
So we used WMAP to evaluate. So for the purposes of this presentation, we used a synthetic data set about 2 million, around 2 million data points, and our metrics of choice was WMAP. So I think like we reached around like our booster trees gave about 0.3334 WMAP error, whereas we are close to 0.45 when it comes to LSTMs.
Okay. Okay.
Right.
Sounds good. Thank you.
All right. Thank you.
Any other views to share from the audience? If you feel like you have something to add, please, yeah, let the speaker suggestions, recommendations from the audience would be appreciated. This is again, as I said, we are like kind of early empirical work doing as far as AI and ML models. So may not be, yeah, we are kind of, yeah, I would say experimenting so far as applications to banking, and the benefits are already, yeah, seen by the model users.
A lot of banking applications. Sorry, this is Jessie. I'm also part of the team. So I used to work in financial services before. So a lot of application in financial services face similar problem in the sense that you have tabular data. A lot of even though you can convert it, it's quite costly to do so in production, right? If you put a deep learning model in production, you're going to have to build a way to convert all this tabular data to tensor at scale as well, which is non-trivial and very costly. You also have the problem of irregular time step when it comes to time series data, which makes LSTM pre-processing really tricky. So I'd be really curious to hear if anyone in the audience has experimented with deep learning architectures with explicitly work well for tabular data. Feel free to reach out offline as well if you have thoughts or comments.
Yeah, absolutely. Yeah, feel free to reach out directly to Jessie, and can take offline some of the discussions around. I guess we should move a bit faster, move to the next speaker.